Hey, good afternoon, everyone. It's my pleasure to introduce Jason Wei. Jason is an AI researcher based in San Francisco. He currently works at OpenAI, where he contributed to OpenAI's O1, which is a frontier model trained to do chain of thought reasoning via reinforcement learning. From 2020 to 2023, Jason was a research scientist at Google Brain, where his work popularized chain of thought prompting, instruction tuning, and emergent phenomena. Welcome, Jason, and I'll hand it over to you.
Great. Yeah, thanks for having me. And the topic for today is going to be scaling paradigms for a large language model. I want to start by saying we've come incredibly far in the past 5 years in AI. So just 5 years ago, in 2019, AI could barely write a coherent paragraph, and it wasn't able to do any reasoning. Today, AI can write an essay about almost anything, and it's also a competition-level programmer and mathematician. Now, how did we get so far so quickly? The thesis that I want to present today is that scaling has been the engine of progress in AI, and it will continue to dictate how the field advances. So here's a short outline. I'll talk for maybe 40 minutes, and then we're happy to take questions after. So first, I'll talk about what exactly is scaling and why do we do it. I'll talk about the first scaling paradigm, which is scaling next word prediction. I'll talk about the challenge with this first paradigm. And then I'll talk about the second paradigm, which we recently entered, which is scaling reinforcement learning on chain of thought. And then finally, I'll conclude with a few notes on how AI culture has been changed by scaling and what we want to see next. So I want to first speak for a few minutes about what we did before this first scaling paradigm. And the reason is you kind of don't realize what's special about your current moment unless you study the past. And so I would say the way that AI progress was made from, say, 2010 to 2017, so basically pre-transformer deep learning, is you have some benchmark like ImageNet, and then you do all these things to try to improve on that baseline. So you have some baseline, and then maybe you can add a better architecture, you add some inductive bias, you build a better optimizer, you do hyperparameter tuning. All these things sort of stack up and allow you to improve performance on your benchmark. And one way you could think about it is you have some XY relationship that you want to learn. And the goal is to learn that relationship as well as possible. And so, for example, a statement of success, sort of in before 2017, would be something like, on the ImageNet data set, our method outperformed the baseline by 5% while using half the compute. But now, with the advent of transformer, we have a pretty good way of learning lots of different types of XY relationships. And if we're not bottlenecked by learning anymore, then what do we do? And it turns out the field sort of decided that the answer to this is scaling. And scaling, very simply, basically in AI just means training a larger model on more data with more GPUs. But I have this more specific definition here, which is scaling is when you put yourself in a situation where you move along a continuous axis and you expect sustained improvement. There's an important part of this definition, which is that scaling is an active process. So you have to put yourself in the situation. Often that involves resolving some bottlenecks or understanding some details about your setup to really get the scaling to work. And here's sort of a typical scaling plot. Your x-axis will be something usually compute, data, or model size. And then your y-axis is some capability that you're trying to improve. And what you want to see is you want to see this blue line where you continuously improve performance as you move along the x-axis. And what you want to avoid is this red line where after some threshold on the x-axis, the performance saturates and you're no longer improving. And to put it very simply, it's not this, but this. And if you look at the seminal, a lot of the seminal works in large language models, you'll see that scaling is everywhere. So here there's a few papers from OpenAI, Google Brain, DeepMind. And you see you can find these scaling law plots in a lot of these different papers. And sometimes you have to flip the plot upside down to find it because loss is being plotted instead of performance. And these plots are really the hallmark of scaling, and they can be very powerful. So at least at OpenAI, if you walk into a meeting with one of these, you sort of know you're going to get what you want at the end of the meeting. One thing to note is that we kind of take the scaling paradigm for granted these days. But at the time, scaling was very non-obvious. And it was non-obvious for many reasons. So first, there's technical and operational challenges that come with trying to scale. First, distributed training requires a lot of expertise. You have to hire a lot of infra engineers to build out this distributed training system. Second, you need ML researchers to fight these loss divergences and hardware failures that might come up. And obviously, number three, compute is very expensive. And in addition to technical challenges, there are also psychological challenges that made scaling pretty hard at the time. So one psychological challenge is that researchers like inductive biases. So there's some inherent joy about having a hypothesis about how you can improve an algorithm and actually seeing better performance on a task. And so researchers like to do work where you change the algorithm. Second, there's always this argument that human learning is much more efficient than scaling. So, a human does not have to read the amount of text that GPT-3 was trained on to learn how to write a paragraph of English. And so there's a question of if humans can do it, why do we need machines to learn from so much more data? And number three, for a long time, and probably still, scientific research incentives don't exactly match all the engineering work that is done as part of scaling. So, when you submit a paper to a conference, they want to see some novelty and not just that you made your data set bigger and you train on more GPUs. So given that scaling is so challenging, why do we scale? And so I want to say, if you're in the not scaling paradigm, almost by definition, each improvement in the model takes some new ingenuity. So you have to spend researchers and to make a modeling advancement. And it's not guaranteed, and it takes some level of creativity. And the second challenge is there are a lot of tasks that we want AI to do. And if you want to train an AI on every single task, it would be pretty challenging. Whereas in scaling-centric AI, by definition, you have a reliable way of improving the capability of the model. Now, the important thing to note is often that's very expensive. So you'll see on a lot of scaling plots, the x-axis is in log scale. So it's actually incredibly expensive to improve performance. But the good news is, if your measure of capabilities, so what your y-axis is very general, then this extreme financial investment can often be justified. And of course, it's hard to talk about scaling without mentioning this essay from Rich Sutton called The Bitter Lesson. And I recommend people to read it if they haven't. It's very well written, and it basically says that general methods that leverage compute are the most effective, and things that scale will ultimately win out. Okay, so I want to talk about the first paradigm, which is scaling next word prediction. And this paradigm started in 2018, and we're still doing it today. And it's very simple. It's just get really, really good at predicting the next word. And I think it's pretty non-trivial to understand this fully. So the question is like, why do you get so much just from predicting the next word? And my answer would be that next word prediction is massively multitask learning. So just as a quick review, the way next word prediction works is you have a sentence like, on weekends, start my students like to. And then what the language model does is for every single word in your vocabulary from, aardvark all the way down to zucchini, the language model assigns some probability of that word. And then the goodness is like how close you are, to the actual next word being 1.0. So in this example, let's say drink is the actual next word. When the language model learns from this, it'll try to increase the probability of drink and decrease the probability of everything else. And I want to show like a bunch of example tasks to sort of illustrate what you would learn just for doing next word prediction on a large enough database. So first, very simply, you'd expect to learn grammar very well. So there's some sentence in pre-training that says, in my free time, I like to. And the next word is code and not banana. So the language model learns that maybe a verb should be weighed higher than a noun here. You would learn things like world knowledge. So there's probably some sentence on the internet that says the capital of Azerbaijan is. And then you learn to upweigh Baku over London. So you learn something about the world. You can learn classic natural language processing tasks like sentiment analysis. So somewhere on the internet, there is a sentence that says, I was engaged on the edge of my seat the whole time. The movie was. And by learning to upweigh good over bad, you're learning something, the language model is learning something about sentiment analysis. You can learn how to do translation. So there's some sentence in pre-training that probably says, the word for neural network in Russian is, and then by upweighing neuronная сеть over привет, you'd learn something about Russian. You can even imagine learning things like spatial reasoning. So, there's probably some sentence on the internet that says, Iro went to the kitchen to make tea. Standing next to Iro, Zuko pondered his destiny. Zuko left the. And then by upweighing kitchen over store, you learn something about the spatial reasoning of where Zuko was. And then finally, you'd expect to learn even things like math. So you might have an arithmetic exam answer key that says 3 plus 4 plus 8 is. And then by the language model learning to predict 15 over 11, it learns something about how math works. And you can imagine there's millions of more types of tasks like this. And by training on just next word prediction on a huge corpus, you're actually doing extreme multitask learning. And the paper that sort of popularized the scaling paradigm in next word prediction is a paper by Kaplan et al. In 2020. And it popularized this notion of scaling laws, which is basically that next word prediction capability or the performance of the language model improves smoothly as we increase the model size, the data set size, and the amount of compute for training. So here on the x-axis is training compute, which is how much data you're training on times how large your model is. And then you can see next word capability goes up. The thing that makes them call it scaling laws is that they can see the trend over 7 orders of magnitude. So they train like language models using 7 orders of magnitude of compute, and they see that the trend holds. And the most important thing here is that it does not saturate like this. So basically, the reason this is important is you should expect to get a better language model if you scale compute. And so that sort of gives researchers confidence to try to continue scaling up. And there's a natural question here of why does scaling work so well? And as a field, I don't think we have a great answer to that, but I can give sort of a hand-wavy explanation of 2 things that you gain from scaling. So first, if you're a small language model, memorization is very costly. So by definition of having very few parameters, you have to be very choosy about what type of knowledge and coding and parameters. On the other hand, for large language models, you have a lot of parameters, and so you can be way more generous in learning tail knowledge and memorizing a lot of facts. Second, if you're a small language model, your capacity in a single forward pass is a lot lower. And so you'd probably be mostly learning first order correlations. Whereas if you're a large language model, you get a lot more compute in a single forward pass. And it's much easier to learn complex heuristics when you have additional compute. Now, one thing you might say is, if scaling laws are so predictable, why were so many people surprised by the success of ChatGPT in the scaling paradigm? And my answer to this would be that next word prediction, because it's secretly massively multitask learning, you'll see that if different tasks arise at different rates, then the emergence of some of these abilities can come out as a surprise. So the way I'd encourage you to think about next word prediction accuracy is sort of as a weighted sum of a bunch of individual subtasks. So you could compute the overall accuracy as sort of I just made these numbers up, but like some small coefficient times the accuracy of grammar plus some small coefficient times the accuracy of world knowledge plus sentiment analysis, math ability, spatial reasoning, etc. And when you look at it in this way, you can ask yourself the following question. If the accuracy goes from 70% to say 80%, do all tasks get better uniformly? So is like accuracy of grammar going from 70 to 80 and math going from 70 to 80? And I would say probably not. So you can look at it like this. So you have overall capability increasing smoothly. For some easy tasks, you're actually not improving performance after some point. So for example, GPT 3.5 basically already has perfect grammar. And so when you train GPT-4, you're probably not actually improving the loss of grammar at all. On the other hand, you might have some tasks that sort of have a big gain in capability. So for example, you could say GPT-3 and GPT-2 are both very bad at math, and they basically can't do math. But GPT-4 is suddenly really good at math. And so you might see the math ability increase in this fashion. And one term that people often use for this is emergent abilities or a phase transition. So you can see there's kind of two phases. So like before the threshold, you're getting mostly performance of 0 or it's very flat. And then once you pass a certain threshold, you see that the performance of the model really starts to get a lot better. And here's sort of one simple example to illustrate emergence. So you could have some prompts like, I like to play soccer and tennis. And then the goal is to translate to Spanish. You can see here there's like 3 models. On the y-axis is the performance on the translation task. Ada and Babbage just repeat the answer because they don't really understand that it should be translation. And you can see the largest model, Curie, suddenly learns to, is suddenly able to do the task perfectly. And the point here is, if you had just trained Ada and Babbage and try to predict whether Curie could do the task, you'd probably be discouraged and say that Curie wouldn't be able to do it. But actually, once you've trained Curie, you can see that the model is able to do that task. And so the way you can think about some of these things is there's a spectrum of possible tasks that we want AI to do. So starting from at the bottom, the most basic ones like returning basic facts or having correct grammar, up to sort of translation, and then maybe writing code, writing a poem, to the hardest tasks like writing a novel or doing scientific research. And the way you can think about it is GPT-2 is only able to do a small set of these tasks. When we get to GPT-3, we're able to do more tasks like translating a sentence and writing a summary. And when you get to GPT-4, even more tasks emerge. It can help you debug code and write a decent poem, and so forth. Okay, so now this kind of raises the question, if next word prediction works so well, as we've seen, can we just scale next word prediction to reach AGI? And My answer would be maybe. It would be pretty hard. We'd have to continue scaling a lot. But there's sort of a fundamental bottleneck with just doing next word prediction. And the bottleneck is that some words are super hard to predict and take a lot of work. So here's an example where next word prediction is great. So the example is, my name is Jason. I'm a researcher at working on large language. And it's very easy to predict models here. But here, there's actually a very challenging example of next word prediction. So it's this math question. And in order to predict the next word, which is either A, B, or C, you have to actually do the entire math task and then map it to A, B, and C. So here, just predicting the next word is very challenging. Another way to think about it is pretend you're ChatGPT. So as soon as you see a prompt, you have to immediately start typing. And so you see a prompt like this, and then you have to immediately say A, B, or C. That'd be a pretty tough task. And what I'm getting at is sort of this. So you can have the difficulty of the task on the, there's a spectrum of difficulties, right? So, there's easy tasks like giving the capital of the state of California. And then there's hard tasks like providing the answer to a multiple choice competition math problem. And the issue with pure next word prediction is you're using the same amount of compute to solve both very easy tasks and very hard tasks. So it's both one token of compute. And where we want to be is actually here. So we want to use a small amount of compute for easy problems and a much larger amount of compute for hard problems like providing the answer to a multiple choice competition math problem. So one approach is chain of thought prompting, which has been something that we've been doing for the past few years. And it's a very simple approach. You just prompt the language model to give this reasoning chain, like almost like how you would show your work to your teacher. And then the language model can actually output this chain of reasoning before it gives the final answer. And turns out this works pretty well. So if you have like a math word problem benchmark, you'll see that if you do chain of thought versus directly answering, you get a huge boost in performance that scales much better with model size. But there is so one way you can think of it is if you've read Thinking Fast and Slow, there's sort of system one thinking, which is next word prediction. So it's sort of automatic, effortless, intuitive, and it's things like repeating a basic fact or recognizing a face. And then you can think of chain of thought as a system two. So whenever you want to do something that's conscious, effortful, controlled, like solving a math problem, then you want to do chain of thought, which is predicting a lot of tokens before getting the final answer. And there's a key issue with chain of thought prompting, which is when you train a model on most of the internet, the reasoning that the model is trained on mostly looks like this. So this is an example of one of my college math homework solutions. And you'll notice that if you think about where this came from, I probably spent like an hour doing this problem on a piece of paper. And then I spent like 10 minutes transcribing it to LaTeX. And then you can see like, the proof, the answer comes at the beginning, et cetera. And so it's really like a post hoc summary of what the actual like internal reasoning process was. And what you actually want the model to do is you want the chain of thought to be sort of like your inner monologue or like a stream of thought. So you want the train of thought to say something like, let me first see what approach we should take. Oh, I'm going to try that. It actually seems wrong. Let me try something else. Let me compute this. Okay, that's the right answer. This is my final answer. And that leads us to the second paradigm, which is scaling RL on chain of thought. And the idea here is you want to train language models to think before giving an answer. And there's an interesting thing here that I'll come back to, which is in addition to scaling compute for training, which is what we've been doing for the past decades in AI, there's a second axis here that's mostly new, which is scaling how long the language model can think at inference time. Of course, we released OpenAI O1, and you should read the blog post if you haven't, but I'll summarize a few key things. So in the blog post, we show a few chain of thoughts that OpenAI O1 gave. When you use it, you'll see like a summarized version, but I think there's a lot to learn from looking at the raw chain of thought. So you could see O1 when it's here, it's trying to do a chemistry problem, and it says first let's understand what's being asked. So it's like trying to make sure it understands the problem. Then you could see that it decides to first try to figure out which ions are present. And then it says like, oh, we have a weak acid and a weak base, but we need to calculate the pH. But then it thinks of like an alternative strategy. And so it says the pH depends on Ka, Kb values. And then it backtracks even more and it says, wait, maybe it's more accurate to find Kb and compare it for NH4. And then it's thinking about, okay, what's the correct formula for this? And it's computing it. And then finally decides that it has the final answer. Another sort of great use case for when you want to do chain of thought before giving the final answer is a class of problems where there's sort of this asymmetry of verification. So what that means is it's much easier to verify a solution than to generate one. So for example, a crossword puzzle, Sudoku, or writing a poem that fits certain constraints. So here's this crossword puzzle. So first, the O1 says, let me think about what could be one across. And so it proposes a bunch of different things. And then once it gets to the one down, then it starts to say like, oh, now let me check which ones could be consistent with one across. And it decides that it's a Another great use case for chain of thought is problems where you know that thinking a lot is crucial for getting good performance. So this is things like competition math or competition code. You can see there's really a huge difference here for some of these things. So GPT-4, which is the teal bar, gets maybe in the tens of % on competition math, competition coding, whereas O1 Preview and O1 are able to do like a majority of the problems. And so it's the difference between basically not being able to do the task versus being able to do most of the problems. And again, in the blog post, we show that pass-at-one accuracy, this is for the competition math data set. As you scale up the amount of training compute, you get better pass-at-one accuracy. And then also, this is the second plot, which is when you give the model more time to think at inference time, it can also have a positive trend with scaling the pass-at-one on this benchmark. Now, I want to talk a little bit about why this paradigm is so special. I think for a lot of people, the reason we're so excited about AI is one day we want AI to help us with the most challenging problems that we face as humanity, like curing disease, the environment, et cetera. And so ideally, in the future, the world we want to move towards is you have a prompt for a very, very challenging problem, like writing a research paper for the best way to make AI safe. And the language model can spend a ton of compute to try to solve this problem at inference time. And so maybe you ask it the question, and then on thousands of GPUs, and a month later, it comes back and it gives you the final answer. And it says, here's a body of work on how to make AI safe. And so the extrapolation that we want to make here is, right now, AI can think for maybe seconds or minutes. But ultimately, we want AI to be able to think for hours and days and weeks and months to help us solve some of the most challenging problems. Okay, so I'll talk a little bit about a few cultural nuggets of how scaling has changed culture around AI research. So one thing is a shift towards data. So again, you're trying to learn some XY relationship with the neural network. I would say from 2010 to maybe 2017, the goal, and even before 2010, was to make this neural network is as good as possible. So like get the best possible performance in learning X, Y. And today, the goal is sort of how do you make the X and the Y as good as possible, because we know we have a good way of learning it. And the example here is basically, back in the day, if you had ImageNet, you'd sort of try to train the best model to get the best ImageNet score. You wouldn't say like, oh, let me make ImageNet 10 times bigger and train a model of that. And nowadays, some really good work comes from just collecting better sets of X and Y. So one example is there's this paper from Google 2 years ago called Minerva. And what they did is they just took an existing language model and they continued training it on like a bunch of math data and archive data. And they found that you could get way better math performance just by doing this continued training on data closer to the domain you're testing on. Another shift in culture is we sort of have this overhang in that we don't have evals that really capture the edge of language models capabilities. So this is a chart I pulled from another talk from David Ryan. And the chart basically shows how fast benchmarks get saturated. So you could see maybe in like the 8 years ago, it would take a few years for a benchmark to get saturated. And then one of the most recent like challenging benchmarks, GPQA, got saturated in around a year with O1. And when David was asked like, oh, are they going to make a harder benchmark? His response is he set out to make the hardest benchmark. And so that's pretty interesting to hear. Another example of AI culture changing is sort of this movement towards a highly multitask model. So in the past, you'd have like one model for every NLP task you want to do. And then now you have a single model that tries to do a lot of different tasks. And you get sort of these weird things where like, the model is a competition level programmer and mathematician, but then when you ask it like 9.11 versus 9.8, it says 9.11 is bigger. And the challenging thing here is you have to measure language models on a lot of different dimensions. And it's pretty hard to say like whether one model is strictly better than another, because there's so many evaluation benchmarks and ways the models can be used that usually you don't have one model being strictly better. Another argument that I hear sometimes is that AI can't do this, so therefore it's not useful. But the way I look at it is that AI doesn't need to be human level on everything. It just has to be really performant on a few use cases to be really useful to humans. And then the final thing I'll say is intelligence and user experience are sort of different axes that you can improve on. So often you'll try to improve a language model by making it way better at, like, say, math and chemistry and coding. But that doesn't mean you'll actually get a model that is a better user experience. Maybe one final shift in AI culture is the shift towards bigger working teams. In 2015, two guys like Dirk Kingma and Jimmy Ba could write the seminal paper that's, I think, one of the most cited papers ever. And nowadays, you need sort of a team of people to build this. So this is the OpenAI O1 team and just a few of the people on the team. If you're Google, you need a lot more people to make Gemini, apparently. And that's the full author list. Okay, I'll talk a little bit about where AI will continue to progress. One direction that I am really excited about is AI for science and healthcare. So I think, as humans, we're okay at doing research, but we have a lot of limitations. So, we can't memorize the internet, and we get tired, we get distracted, etc. I think AI really has a lot of potential to help us in scientific and medical innovation, because it can learn almost anything, and it doesn't get tired. It can work for a long time. Another direction is more factual AI. So right now, ChatGPT still, I'd say, hallucinates more than we want it to. And ultimately, I think it's possible to get to a model that very rarely hallucinates, is really good at citing sources, and is very calibrated. I think we're going to move towards a lot more multimodal AI. And so, text is a really good medium for learning because it's such a compressed representation of our world. But we're going to move towards AI with, Sora and advanced voice mode that is way more integrated into our world. I think tool use will be another big one. So right now we have AI as sort of like a chat assistant where you can reach out and it'll answer a question for you. I think eventually we want to get to a state where AI can take actions on behalf of users and also show initiative to talk to users. And then finally, I think we'll see a lot of AI applications. So I feel like there's always this overhang between the state of the art of some technology and when it actually gets deployed. So, for example, in San Francisco, Waymo sort of works in one of the hardest driving environments in the world, but we still haven't deployed Waymo. Like Google hasn't deployed Waymo to most of the world yet. And maybe another example is like I feel like right now AI is good enough to like take your order at a restaurant, but it still hasn't been applied for that yet. Okay, so I'll revisit the first plot, which is in 2019, AI was very limited. Today, it's pretty capable. And I'm very excited for where we'll be in the next 5 years. And I want to encourage everyone to think about it. And I'll end with this. So when Nemo doesn't know what to do next and he's in a tough spot, Dory says, just keep swimming. I will say, just keep scaling. Thank you for listening. Happy to connect on Twitter. If you're interested in OpenAI, please reach out. And I also have a feedback form for any feedback on the slides. Thank you. Yeah, so I'll take questions now.
I will also add that there will be a reception after the talk with
Yeah, what's up?
Yeah, so thank you for the talk and the meets. I noticed you mentioned like next word prediction for both the spatial reasoning as well as the tool use for interaction with the real world. Problems like contact modeling are really hard to do even in simulators.
Yeah.
Do you think that we're just waiting for like a phase transition or like a grokking style behavior for spatial reasoning? Or is there something more to it than just next word prediction?
Yeah. I feel like your example is one of those things that people might think would happen, but the way you can think about it is the internet actually captures a lot of different types of information, but you do have to make sure that like the data you want is somewhere on the internet, otherwise it won't be trained on. So like I feel like the like surprisingness of emergence isn't that language models like suddenly became super capable. It's that people underestimate what type of data is on the internet and like what you would learn from like putting a lot of optimization pressure on just predicting the next token. So I think in your case, it would have to be something where like people intentionally generate maybe synthetic data and train a model on that to get that ability. Yeah.
So I just have thanks so much for the great talk.
Yeah.
I just have a really quick question. So since generic mathematical reasoning is like an big problem, I was wondering how feasible you think scaling at inference time would be, given that we potentially need to scale exponentially in our context.
Yeah, I mean, it seems possible. It's hard to really predict the future. I think if you look at the trends, the context windows have really increased by a lot in the past few years. So I think in say 2022, having like a 4K context was like pretty good. But nowadays we're at like 1 million plus context length with Gemini. Yeah, I think there's like headroom. I don't know, like maybe the cost comes into play at some point where you're like, okay, to solve this problem, we don't really have enough GPUs to do that, and we're not sure if it'll even work.
As a follow-up to his question, so let's say you build an AI which is really good at calling tools, like in his case, a SAT solver.
Yeah.
Would you count that as a success of
AI scaling, or when you say scaling, you literally mean just next word prediction?
I would count it as a success. I don't know about like whether people really try to assign it to data scaling or not.